now I'm going to go through the construction of the projective plane, and I'm going to explain how this is related to the quotient topology and to plane models that we've learned in week 1. Okay? So what is the projective plane? So the definition of the projective plane is that the projective plane, well, it is a very strange object. So this is the set of one-dimensional subspaces of the 3D space, right? So this is the set of, or in other words, we can say that this is the set of lines in the 3D space in R3 that pass through the origin. Right? So passing through the origin 0, 0, 0. So how can we think of this in terms of the quotient topology? Now, well, let's think of a point in the space with coordinates x, y, z. So suppose that we have a point with coordinates x, y, z. Then what is the line that passes through this point and the origin? And so what is, so think of this straight line. Let's say L. So what is this L? And since this line is a one-dimensional subspace, so it means that this L is the set of, is going to be the set of points that are obtained from the point x, y, z. So if this is the point x, y, z, by multiplying with different constants. So it's going to be the set of points that look like this: lambda x, lambda y, lambda z, for different values of lambda. So for all possible values of lambda. So for example, if this is, I don't know, the point 1, 2, 3, then if you multiply 1, 2, 3 by, say, 1/10, 1/10, 2/10, 3/10, or if you multiply it by, say, -2, so -2, -4, -6, these 3 points and the origin, they belong to the same line. Right, so all these, they represent the same point of the projective plane. Well, but then you can construct the projective plane as the quotient space. Right, so we can introduce the following equivalence relation on R3. So we can say that two points of R3, x, y, z, are equivalent to each other whenever one of them can be obtained from another one by multiplying x, y, and z with lambda. So x, y, z is equivalent to lambda x, lambda y, lambda z. Well, it is important to understand that 0, 0, 0 should not be allowed. So it is actually an equivalence relation not on the whole R3, but on the R3 without the origin. And lambda shouldn't be equal to 0, right? So then this construction of the projective plane is just the quotient space of R3 minus the origin with respect to this equivalence relation, right? So the projective plane, I'm going to denote it by P, is going to be R3 minus the origin quotient space with respect to this equivalence relation. So this equivalence relation tells us that two vectors that are proportional to each other are equivalent. So whenever they are proportional to each other, they are equivalent because it exactly means that two vectors that belong to the same line that passes through the origin are equivalent. So in other words, this equivalence relation, so every equivalence class with respect to this equivalence relation is exactly one line, right? So Now, let me introduce a notation for an equivalence class. So the standard notation uses so-called homogeneous coordinates. So when we write x, y, z with colons and with square brackets. So this is the equivalence class of x, y, z. So this is the set of all lambda x, lambda y, lambda z, where lambda is not 0. So this is the equivalence class of a point x, y, z, and this is at the same time the straight line that contains x, y, z. And so this is the standard notation. Now, how can we actually see that this is a surface, and how can we represent it as a plane model, right? So now, how do we see that it's a surface? So is this really a surface? Well, so what's a surface? A surface is characterized by the fact that every point has a little neighborhood that is homeomorphic to a disk in the plane, or maybe even the whole plane. So now, watch this. So if we have a point of the projective plane given by homogeneous coordinates x, y, z, then remember that x, y, z are defined up to multiplication with any constant. So it means that I can multiply all x, y, and z by, say, 1 over x. And this is going to be 1 y over x, z over x. Of course, it's only going to work if x is not 0. Okay? So if x is not 0, then we can see that our point is equivalent to the point with coordinates 1 y over x, z over x, and then we can call this u, call this v, and then the point uv is a point on the plane, and we see that the set of all points of the projective plane such that x is not 0 is going to be homeomorphic to the whole plane. But of course, by the same logic, the set of all points x, y, z where y is not 0 is also going to be homeomorphic to the plane, and same when z does not equal 0. But since at least one of the three x, y, z has to be non-zero, it means that all points of the projective plane, they have some neighborhood that is homeomorphic to R2. So which means that this is actually a surface. Well, but if this is a surface, then it means that we can represent it by a plane model. So how can we represent it by a plane model? Well, let me erase this. And let us consider some point on the projective plane given by homogeneous coordinates x, y, z. So remember that these are defined up to multiplying with a constant. So that constant can be 1, 2, 3, negative 10, 1 over 10, or it can be something in terms of x, y, and z, like in the previous example it was 1 over x, and so on. Well, what I'm going to do, I'm going to choose a particular representative of this equivalence class that is on the unit sphere. So choose a representative. This is an equivalence class, so this is the whole line. And this line is going to intersect the unit sphere at 2 points. Right? So I'm going to instead of thinking of the whole line as the equivalence class, I'm going to choose just one of these 2 points that belong to the unit sphere. So I'm going to choose a representative on the unit sphere S2. So S2 is the unit sphere in the 3D space. So how do I do it? That exactly. So I'm going to multiply. I'm going to normalize the vector x, y, z. So I am allowed to multiply this by any number. So in particular, I'm going to multiply it by 1 over square root of x squared plus y squared plus z squared. So what is good about it? So now what it tells me is that instead of every equivalence class consisting of a whole line, so now every equivalence class it has just 2 points that belong to the unit sphere. And of course it is easier to deal with 2 points than with infinitely many points. But that's not all. So notice that I can continue, and what I am going to choose is not just either of these 2 points, but I'm going to choose, strictly speaking, there are 2 opposite points on the unit sphere that every line that passes through the origin goes through. Well, but then I'm going to choose one that is in the lower hemisphere. So in other words, so I'm on all two possible versions of this. I'm going to choose the one that has non-positive z. So I'm going to write that z is going to be less than or equal to 0. Right? So every equivalence class, that is a line that passes through the origin, it has 2 points on the unit sphere, and among these 2 points, one belongs to the lower hemisphere. Right? So it looks like this. So we have our coordinate system, x, y, z, and then I'm going to have a lower hemisphere. So this is going to be x, y, z. This is 1. This is 1. Negative 1, negative 1. And now every line that passes through the origin, for example, that L. So if I draw a line that passes through the origin, then it's going to intersect my lower hemisphere at some point, and this point is going to be the sort of the chosen or the selected representative of L. So this ends L. Well, which means that seemingly it kind of looks like the projective plane is just the lower hemisphere, but it is not exactly true. So because some lines that are here, they are going to be exactly horizontal, right? So if z is negative, then there is a unique representative of the class, right? So if z is negative, then such a representative of a line is unique. But if z is 0, so then if z is 0, then our line L, it is exactly horizontal, right? So it does not go up or down, so it is entirely in the plane xy. And then it's going to intersect. So let me draw some horizontal line. Then it's going to intersect the sphere at 2 points. And notice that these 2 points are going to be opposite points. And these 2 points, they are both representatives of the same point of the projective plane because they represent the same equivalence class. But if they represent the same equivalence class, it means that they're supposed to be glued. Right? And they are always going to be opposite. So it means that if z is 0, then opposite points are to be glued. So what we have shown is that the projective plane can be represented by the lower hemisphere such that on the boundary of this lower hemisphere, on the circle, all possible pairs of opposite points are to be glued. So let me draw it. So it is a lower hemisphere, and on the boundary, opposite points are to be glued. So this point is glued to this point. This point is glued to this point. I don't know. This point is to be glued to this point, and so on. So all pairs of opposite points are to be glued. But the funny thing about it is that the lower hemisphere is, of course, homeomorphic to just a disk. And if you think of the rule that you get when you say that opposite pairs of points are to be glued to each other, then this is exactly the same rule as the rule given by these labels on the two edges. Because if this is A and this is A, right? So then what it tells us that we need to glue this A to this A with a twist. But then it exactly means that this point is to be glued to this, this to this, this to this, and so on. So which means that the projective plane that we initially identify as the set of lines in the 3D space that pass through the origin, or equivalently as the set of one-dimensional subspaces of R3, we can define it in terms of the quotient topology. So the quotient topology is that we define an equivalence relation on the set of R3 minus the origin, and that equivalence relation tells us that 2 points are equivalent whenever they belong to the same straight line. And then when we kind of think about it and try to simplify it, then we see that every equivalence class, it has two sort of selected representatives, and among the two, usually we can choose just one. So with such that it belongs to the unit sphere and to the lower hemisphere, so that is negative. But for some cases, when that is exactly 0, we cannot choose one of the two. And since we cannot choose one of the two, we kind of choose both of them to represent that equivalence class, but then it means that we have to glue them. And this is exactly the same as gluing according to this instruction, A here and A here. And this is why the abstract projective plane that is identified as the set of one-dimensional lines in the 3D space can be also identified with this surface and this plane model.